kind of initiated the discussion trying to motivate why mathematical physics is important, interesting, and what is the mutual connection between mathematics and physics per se, how they have co-evolved. And eventually we, like towards the end of yesterday's discussion, I started with some very basic ideas which every physicist who is working, like who is trying to practice physics as a profession, must be aware of. And like, so basically what we were talking about is physicists' basic toolkit. And there we saw yesterday how data visualization is crucial. And given a function, how we go about understanding its threshold behavior, its asymptotic behavior, if there are zeros, if there are maxima, minima, if there are inflection points. Okay. And based on that, like we also tried to see how modern softwares could be utilized for like data visualization. So they're really just like calculators being used for multiplying large numbers, right? So we saw some primitive examples there, and eventually as the course progresses, you will be able to see more. We also talked about item number 3 here, where we are talking about order of magnitude estimation. So we also discussed this a little bit yesterday. Today we will be talking about dimensional analysis and scaling arguments, and like overall the idea would be how do we get insights out of this, and couple of additional stuff. So maybe in the next class we will see beyond this top 4 items how physicists gain insights about a given problem by looking at inherent features which are embedded within the problem. So suppose at many times there are isometries, right? Or there are symmetries that the physics problem has. So how one can develop additional insights from that. So it turns out these top 5 skills, like within this topic 0, are crucial for uh, most practicing physicists, and also therefore for mathematicians interested in applied physics. Okay, so that's the reason why we are discussing. So although it may look a little mundane at times, but it is better than done once rather than left completely. Okay, in a given course, it's quite possible that many of you would have come across excellent teachers in past, and they would have emphasized these points clearly. But I don't want to leave room for benefit of doubt here. So therefore I decided that let me start with this before getting into core mathematical physics. And uh, uh, probably we will be starting with linear algebra soon, like once these preliminaries are over. Yeah, so what is dimensional analysis? I think it's a kind of question which you would have answered many times since you're +2. So basically what we are trying to do is look at how a physical quantity depends on other, preferably more fundamental physical quantities in a given scenario, right? And this basically involves analysis of the relationships between different physical quantities and their fundamental dimensions. Like, so here I would like to emphasize that students generally are aware of mass, length, and time, but the IUPAP, which is International Union of Pure and Applied Physics, they have come up with this guideline of 7 fundamental dimensions or 7 fundamental units. They include length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity or candela. So like this is something that you have to be aware of, and any physical quantity that we come across, we should be able to express them in all these fundamental dimensions. So let's see, for example, like there are two quantities which we use very often.
Excuse me,
Huh.
sir.
Hello,
Hello.
yes,
Yeah,
yes,
this is Babaji Chansah, sir. I have a doubt
hello.
from my plus two time, sir. Yes, sir. This is
Please,
Babaji Chansah. Yeah.
please tell me.
Yes, sir. Why electric current is fundamental, not charge, sir?
Not charge. Okay, that's about a choice. I
Yeah.
will come to it. I will come to it. Huh? Later
Okay, sir.
in
Thanks.
this talk, I will come to that point. Particularly, I will show you
Okay, sir.
what IUPAP considers as fundamental units, and what is the basis for that. Some kind of, it may
Okay,
in
sir.
fact be initiated as a question in the beginning, and I may come slowly to this answer, but eventually rest assured,
Okay, sir.
your whatever confusion, since whatever plus two, that would be cleared, like within maybe
Okay,
one or
sir.
2 days, within 1 or 2 days. But let us go with the flow,
Okay, sir.
because that is part of the
Okay, sir.
climax. That's part of the climax. Okay, so we need to be holding on to it for the moment. But thanks for
Okay.
raising this question. Very good.
Hello, sir. I'm Sonu,
Huh.
sir.
Thank you,
Yes,
sir.
Sonu.
Sir,
Sonu, tell me.
actually, you just said that the third topic, order of magnitude estimation, was covered in last lecture, but it was
Yes.
not covered in
No, it
yesterday's
was,
lecture.
no, it was covered when we, if you recall, we were talking about, say, suppose you are estimating volume of the room in which you are staying.
Oh, that's
Right,
okay. Okay,
right,
sir.
right.
Yes.
So we were like, you have to be careful about, and if you recall, we discussed about how to have a physical feel for various quantities, like 1 Newton. What
Yes.
is 1 Newton, and so on.
Yes.
So we did cover. The point is, there would be assignments which will further delve into this, and by the end of this week, we will be thorough with these items.
Okay, sir.
Okay, so if all of you allow, I will kind of proceed. Yeah. So here, like most of you would have used degrees as in sine theta, right? The unit of theta, as well as radians. Okay, so when we use these units like radians, like that is for plane angle, and steradian, which is for solid angle. So these are typically dimensionless units. Okay, but still they are fundamental, means they are fundamental to our understanding of various quantities, and therefore I have kind of placed them here. And these are a set of derived units which are obtained from the 7 fundamental units I just mentioned. Okay, so you will have to be aware of radian, steradian. So radian is basically, if I am trying to look at a given angle, right? And I say the angle is 1 radian if the length along the curved region and the length along the straight region, if they are identical. Okay, so that is basically equivalent to, this angle would then be equivalent to 1 radian. Right. Similarly, when you say steradian, you can imagine a unit sphere, and then on that, like figure out a curved area, or which is unit area, right? And then from that unit area, unit circle, some kind of a circle which has an overall curved area which is 1 unit. So from there to the center of this unit sphere, if you try to etch out a cone, so that would roughly be 1 steradian. So it's like, if you imagine this to be a sphere, then I have a unit area, right? And then I kind of etch out from the center. So this would be like, this solid angle would be about 1 steradian. Okay, same way there is hertz, which is per second. There is Newton, which you are aware of, which is 1 kilogram meter per second square. There's Pascal, which is unit of pressure, that is force per unit area. So accordingly, we see it as Newton per meter square. There is Joule, which is essentially Newton times meter or force times displacement, and that is the unit of not only energy but also for work and as well as for heat. So you will see that in physics, when we are handling quantities like energy, work, or heat, they are having similar dimensions, same dimensions. Right. Then the another unit is watt, which is basically rate of doing work. So you can take the unit of energy and divide it by unit of time. So that would be typically unit of power. And similarly, you have coulomb, which is ampere second. We will come to Babula's question later on. And then there's volt, which is electrical potential difference, right, or EMF, and that is basically watt per ampere, right, or joule per coulomb. So similarly, farad is the unit for capacitance, and ohm is the unit of resistance. Sievert and like Sievert is a unit of like radioactive dose, right? So therefore it is represented as per meter square per second square or joule per kilogram, like these kind of a thing. And kettle is a unit of catalytic activity. There are few more important quantities like Siemens, which is unit of electrical conductance, Weber, which is unit of magnetic flux, Tesla, which is unit of magnetic flux density. So please make sure that you, for this class, you keep this in mind, that Tesla is unit of magnetic flux density. We will be coming to a particular question like which we'll try to address soon. Henry is a unit of inductance, and degree Celsius, or basically Kelvin, is the unit of temperature. And Kelvin and degree C are related via a kind of linear relation where Kelvin is essentially like, say, when we are saying 0 Kelvin, so 0 Kelvin is about minus 273.15 degrees C. So it is 273.15 degrees C below the freezing point of water. So similarly, lumen is the unit of luminous flux. Lux is the unit of illuminance. Becquerel again is the unit of radioactivity, and Gray also for unit of radioactivity, and Sievert also unit of radioactivity. So these are at most the units which in general you will be coming across while dealing with various physical quantities. And it's not bad to once revise them. So I would be sending you these PPTs so that you can go through it. So now, like coming to the question which Babula had asked, so it turns out in 19, like basically 2019, IUPAP eventually decided that uh, like most of the standards, like basically we had standards of mass, standards of time, standards of weight, which came about by keeping standard quantities. Like basically they will keep in general in Paris there is a IUPAP headquarters, so over there they will keep a standard rod of a given length, and that they will standardize as a meter. Why this is important? Because eventually all the distances have to be measured in that primary standard, some kind of a primary standard which is maintained by IUPAP, and copies of it is circulated to various governments to make sure that they have identical units for meter across the world. This really helps because eventually it would be really silly if different countries have different meters, because then distance between two countries in a flight would be really absurd. Like you will have no way of obtaining it. So in 2019 they decided to get rid of these standards. So basically this rod which was kept, or a later innovation of that where they were looking at wavelength of a particular light and counting number a certain number of wavelengths and saying that would be the unit of meter, right? Or that would be the standard meter. Even they got rid of that, and they decided that they would have interferometric way of looking at a meter, and then speed of light would become essentially the standard estimate. So what they would do is they will have devices which would be able to measure the time which light takes to move from one location to another location, and accordingly they would come about with these three quantities. So speed of light would be one quantity. The other one is frequency. So this is again from quantum mechanics, and constant again from quantum mechanics. So basically now the standards on which all the units are dependent are going to be speed of light, frequency of a particular like cesium 32 atom. So basically there is a specific light which is emitted when there is a transition happening from a higher energy state to a lower energy state in cesium. And similarly, like there is a particular vibration frequency, right, corresponding to that light, that color. So this vibration frequency, a certain number of these, like, so this is the number goes something like 9192650,763.73 vibration or something like that. I may be a little wrong in exactly quoting this number. So that many vibrations of this cesium atom would correspond to basically 1 second. And once you know this seconds and you know speed of light, then you would be able to estimate meter, right? Similarly, like in order to standardize kilogram, now the standard weight which was kept under lot of protection, right, that is no more required. So earlier this weight was kept uh, keeping all precautions so that there is no corrosion, no kind of effect on that mass due to radioactivity, no effect on that mass due to other physical factors, right? So however, that was really a very complicated task. So therefore they eventually settled down on Planck's constant. So this is really beautiful how, and now we need to worry only about speed of light, frequency of vibration of cesium atom, and ways to measure Planck's constant. So in all these three, like special relativity and quantum mechanics are at core. So basically now these are really modern way of defining fundamental units like meter, second, and kilogram. Now it turns out, because second is more fundamental, that's the reason why electronic charge cannot be kind of. So basically what one does is, instead of taking only like electronic charge as a fundamental unit, because second is measured with much more accuracy and charge can be measured with a higher accuracy. See, when you are measuring like current per se, right, and if you try to kind of measure it using a given tool, right, it may be a difficult task. However, in order to keep this connection to second alive, because second is considered to be a more fundamental unit, eventually they decided that ampere would be at the core. So of course, when Babula says that charge is supposed to be more fundamental, definitely yes. So it is at the level, same level as speed of light or frequency of cesium atom or Planck's constant. So indeed, that is more fundamental. Okay, but for convenience, like what one is doing is, instead of keeping the speed of light or Planck's constant or frequency or electronic charge, or for that matter Boltzmann constant, or like a constant associated with illuminance or Avogadro's number, right, they decided to settle down on this central core seven quantities. Babula, is that fine? right? So now these 7 quantities are on same footing now, more or less, except that there are arrows connecting. And today's exercise is primarily what is the significance of these arrows and find out. So this is basically the homework for today. So this would be the TOD today. TOD today. So task of the day 02. Right, so you will have to read a little bit, and I will be sending some interesting article or relevant material to you. And what you will have to find out is why these arrows, why the arrow goes from second to everything. Right, you can see the arrow goes from second to everything except mole. Right, and then similarly the arrow from mass goes to like the arrow from m meter, like length, goes to kilogram, goes to candela, goes to Kelvin. Right, so what is the reason, what is the physical significance of that, that you have to kind of bother about. But this is how the central core is the set of fundamental units that IUPAP has essentially come up with long ago, and in 2019 they have decided to have Planck's constant, frequency of vibration of cesium, and speed of light as the core physical quantities which must be measured to standardize kilogram, second, and mass respectively. Okay, the other quantities have remained identical. So Avogadro's number, the constant related to illuminance, and Boltzmann constant and electronic charge, they have remained identical. And however, like now, from modern physics, Planck's constant, speed of light, and frequency of vibration of cesium are the measurable quantity based on which the fundamental units would be standardized. Okay. So now let me come to these dimensional formula, the idea of dimensional formula. So when we say speed, we know the speed unit is meter per second, and accordingly the dimensional formula has to be length per time, which is kind of easy. Same way, momentum has to be mass into velocity. So momentum is basically P is mass into velocity. So therefore kilogram meter per second, and accordingly the dimensional formula is mass length per time, which is again easy. Force is mass into acceleration, and acceleration would be say meter per second square. So therefore like the dimension would be mass into acceleration, which is length per time square. So the way speed has length per time, acceleration is length per time square. Similarly, when we are looking at surface tension, this is force per unit length, right? And accordingly, like you will have to take away this length. So therefore, you know force and surface tension also. And there are many more quantities in mechanics for which dimensions you can obtain very easily. Now my question is, how would you obtain permittivity of free space? So permittivity of free space has a symbol epsilon 0. So how would you obtain this? So of course, students who have like studied these things in plus 2 and MSc or
Sir,
BSc,
from Coulomb's
huh,
law, sir.
from Coulomb's law, excellent. So what he is
Coulomb's law.
saying,
Yes.
so what he's saying is, say suppose we have force between two charges, right, given by 1 over 4 pi epsilon 0 q1 q2 by r square, where q1 q2 are the two charges, r is the separation between the two charges, and epsilon 0 is this permittivity of free space, and f is force. So therefore, if we know dimensions of force, then we will be able to and if we know dimensions of charges, dimensions of lengths, then we will be able to estimate dimension of epsilon 0. So basically epsilon 0, the dimensional part is going to be inverse of force, right, because that will go in denominator, And then we have ampere square second square, right? So ampere square times square, because this is Q1, charge is current times time, and then divided by length square. So if you now try to look at it, so this is like mass inverse, length inverse times square. This is force inverse times ampere square times square and divided by length square. So therefore you can see that this indeed goes over to this, right? So you are essentially having, let me see what is the problem here. Mass length per time square epsilon 0 would be 1 over force. So here it is going to be -1. Is that the case? So this is going to be mass inverse, length inverse cube, time 4 ampere, time 4 ampere square. Yeah. So this is essentially mass inverse, length inverse cube, time 4 ampere square. Similarly, if I ask you a question, how would you estimate permeability of free space? How would you do that? So somebody else? So I think at the moment I will not be asking. Somebody from maths would like to attempt this.
Mu naught, I think mu naught is permeability.
Yeah. So the okay, of course, that is right.
I think from the magnetic field, I think.
So that is right. So you are saying from magnetic field. Okay. So very good. So what you have said is correct. So suppose we are having magnetic flux density, and that is connected to magnetic field strength H. Okay. So that means this mu naught would be basically magnetic flux density divided by magnetic field strength, right? So magnetic field strength of course has a very simple kind of unit, which is ampere per meter, right? So therefore we know that the dimension of H is going to be ampere and length inverse in this nomenclature. But now how would you find out magnetic flux density? So we have to again recall our +2 know-how, where force was the force on a current carrying coil was given as Bi times length, right? Some kind of a formula with maybe a sine theta involved, right? So therefore B is the dimension of B is going to be dimension of force divided by dimension of current and dimension of length, right? So therefore this is like mass length per time square divided by, so ampere second, so ampere time and times length. So this is like mass per time square, length with cancel, per ampere, something like this. Yeah, mass into acceleration divided by ampere time per
Time inverse
huh?
3.
Force is
Time
going to
inverse
be
3.
time inverse also, time inverse
Yes.
3. Very good. Time inverse 3, right? So now if this is B, so therefore dimension of mu is going to be dimension of B by dimension of H, which is going to be mass time inverse cube ampere inverse divided by, so this is ampere per meter, so basically length inverse. So therefore this effectively goes into mass to the power 1, length to the power 1, time to the power uh, just a second, ampere per meter, mass length per, Okay, so time cube, right? Yeah, okay. So there is a possibility that whatever I have written down here may be okay. Ampere square.
Sir, in
Huh,
sir,
huh.
sir, in the
Yes.
dimension of b,
Huh.
there is not t in the denominator, maybe.
In the denominator, no, there is, right? I would be. I would be. Yeah, this is not there. Very good. So because we have I current, right? Very good.
Yes, sir.
So this was meter square. Okay, very good. Fine. So therefore we will have time inverse square and ampere minus 2. So the whole idea is that these kind of conversions you should be comfortable with, because this is very much required, and particularly like any physical quantity that you state, if you are not putting a unit in front of it, and if you are not having some kind of an idea about its dimensions, like developing a physical feel for that quantity is not possible. So therefore I thought that this is something which we must discuss. Okay, so there would be few problems again related to this thing, which I hope you will be solving. Okay, so this so now I would like to come to another issue, like which is the main strength of dimensional analysis. And here I am just showing some image from a recent work which a PhD student working with me and one of my colleagues in mechanical engineering department is doing. So there what we are trying to do is we are trying to make surfaces which are super hydrophobic. Okay, and that is with a purpose which is very interesting, which maybe some other time. But at the moment, the thing which is relevant for our problem is try to see the time it takes for the object to go from maybe scenario this to, so basically what happens is a droplet is impinged onto the surface, and then that droplet undergoes deformation, right? In so basically from here it will undergo deformation, and then it will come back to its original shape. Okay, and the time which elapses between this, like from the initial time to this, is a relevant quantity. Okay, so this time we need to estimate. Okay, everyone got the question, right? So we need to estimate the time, and there are interesting theoretical works which are proposed how to really go about estimating this time. And like accordingly, a kind of formula is obtained by maybe Lee et al. I will not write down the reference here at the moment, but what they do is this tau actually goes something like 2.6 plus minus 0.1 times rho r cube by s. Okay, so this is a formula which is obtained for estimating the time from a droplet which goes and impinges onto a surface back to its normal shape. Okay, and this is something which, like, people after a lot of at least 5 pages of algebra, like serious algebra, and lot of microscopic understanding going into it, and the final formula which is obtained is this. Okay, so this is an interesting formula, right? However, the point which I wanted to make was, like, using dimensional analysis, one can obtain such a formula even without really knowing the underlying physics, right? We need to really worry about what are the important quantities here. For example, we see that this kind of impingement is happening on all surfaces, right? All kinds of surfaces. And accordingly, like, we would like to see what is fundamental to this problem. So we find that the density of liquid is one quantity which is important, right? So this is one quantity. The other quantity which is important is this radius of this drop, or the diameter of this drop. And the third quantity which is important is surface tension. Say for example, when we are impinging water droplets, it shows a slightly different time than suppose when we are impinging alcohol drops, or when we are impinging benzene drops, right? So therefore these three are fundamental to the like underlying physics. So what we propose is that this tau is some constant times rho to the power a, r to the power b, s to the power c, right? And therefore the claim is, like, if we can find a, b, c, we can find the dependence of tau on rho, r and s. Okay, and you must have solved this problem earlier, but anyway, for sake of completeness, let's do this. So this constant is dimensionless, it's a pure number here. So therefore, what we want to do is we want to see it as rho to the power a, r to the power b, s to the power c, right? And we know that the dimension of rho is mass per length cube, r is length, and surface tension is force per unit length, right? So this is like mass per time square to the power c, right? And therefore this goes into mass to the power a plus c, length to the power minus 3a plus b, and time to the power minus 2c, right? And on the left hand side, it is simply time. So this simply implies that a plus c equals to 0, 3a plus b equals to minus 3a plus b equals to 0 again, and minus 2c equals to 1. So therefore that implies that c is going to be minus half. If c is minus half, then a is going to be half, right? And therefore b is going to be minus b is going to be
By 2.
b is going to be
3 by 2.
so 3a, so this is going to be 3 by 2. Excellent, huh? So therefore, like, even without really doing any like solving any differential equations, or solving any, setting up any boundary conditions, or like doing any such complicated calculations, we have come up with a dependence which is a is half, b is 3 by 2, and c is minus half. So that simply implies that tau is going to be constant times root over rho r cube by s. So that's the strength of dimensional analysis. Of course, the point is like, this cannot be ignored, that obtaining this prefactor 2.6 with this error bar plus minus 0.1 is very crucial. It's not very easy, huh? However, and it's very important at the same time. But the point is that you get some very useful insights without really doing very difficult calculations, right? By looking at fundamental quantities which may be affecting the properties. So over here, for example, suppose you used viscosity also, right? Eta also. So this can be tried by like some of you. So you can say, suppose you put eta to the power d, you will find that d will turn out to be 0. Like if you take eta as the fourth quantity. So however, if you take eta, rho and r as 3 quantities, eliminating surface tension altogether, then you may have an eta dependence coming in. That need not be the right version of the solution, But who knows, maybe under certain physical circumstances, it is viscosity which dominates surface tension. Okay, so therefore, like this dimensional analysis is something which I would like all of you to be aware of. So now we come to this notion of scaling analysis, and for that, let me just switch to another kind of medium which I have already kind of made. And I would like to motivate the scaling analysis through a interesting problem of miniaturization. Fine. So here the point is that we are trying to go from macro to micro scale. So macro to micro scale means we are going from sizes which we can physically see with naked eyes to sizes where we cannot see things with naked eyes. So here, like I would use this as a paradigm system for understanding the scaling analysis. Huh? So I can ask a typical question, like many of you would have seen that, uh, like if you take breadcrumbs and if you take a comb and if you simply comb your hair for several times, there is static electricity which is developed and breadcrumbs are attracted. But the entire bread loaf is not attracted, right? The reason being the dimensions of breadcrumb is such that the charges which are picked up on a breadcrumb and on a comb, like they are just sufficient for leading to a effective force which is going to lead to the attraction between these two objects. Okay, so now so the answer is mass is smaller and there is much more, and that much more is to do with the surface charge on the surface, right? So electrostatic force, so that more is this idea that electrostatic force is proportional to charge on the surface. So for a breadcrumb which is smaller in size, the surface to volume ratio is much larger compared to bread. Okay, and that is typically leading to this phenomena. So what next I illustrate is a simple problem where we have a 10 centimeter side cube, and what we are trying to do is we are trying to compare it with a 0.1 centimeter side cube, right? So basically for a 10 centimeter side cube, like the surface area is 6 times length square, so there are kind of one surface, two surface, three surface, and overall three more hidden surfaces, so there are 6 surfaces, right? So therefore volume would be going as length cube and surface will go as length square, and therefore volume per surface, like going as length square, but then there is the actual surface is actually 6 length square, so therefore volume over surface goes as a number which is 1.6. Whereas the same quantity, when you scale down the object, you have to understand that this object and this object are isometric to each other. There is isometry, right? The shape is not changing, only the scales are changing, the lengths are changing along all the three sides. Huh? So here you can see this volume per surface is about 0.016. So as size decreases, volume goes down faster than surface. Okay, so this is the implication that we can find out of this. So what happens is as size decreases, volume is going down faster than surface. Now inertia of a given object, that is the amount of matter which is contained in a particular object, is proportional to volume, and the proportionality constant is density, right? We all of us know that mass is going to be density times volume, right? So therefore mass is proportional to volume, right? So now as volume goes down faster, so therefore inertia goes down faster. Now the claim is it goes down faster than electrostatic force. So these kind of a statement can be derived from scaling analysis. Okay, and this has lot of useful implication. Although I have not yet shown how electrostatic force goes slower than mass, we will soon see that. Uh, but these kind of statements, like these are what we know as insights. So when you look at a particular physical phenomena where sizes are going down, like you are going from macroscopic dimensions to microscopic dimensions, you can straight away make comments about fact that inertia becomes less important than electrostatic force. And that is the reason why like there is specific know-how, specific set of know-how which goes into designing these accelerometers. Okay, accelerometers have the bulkiest element, which is a large size proof mass, and that large size is maintained just because if a smaller size is maintained, the inertia is essentially ineffective, right? So that proof mass is connected to something known as comb drive, right? So like in an accelerometer, therefore, like this kind of a simple heuristic analysis based on scaling can lead to profound implications. Okay, so therefore, like a statement, another statement which can be made is decrease in volume by surface ratio is a crucial factor in a design of the so-called, so when we say MEMS, we are talking about micro electromechanical systems. So many of you who are working on in applied maths, like now for students, you may come across a scenario where you are actually supposed to model something as complicated as this, a micro electromechanical system. But then it turns out simple arguments from scaling analysis can take you a long way. Huh. So at a certain degree of miniaturization, surface effects will start dominating over volume effects. So that is very important, and that kind of sets scale for what would be the typical sizes at which you will have to limit your MEMS devices. So let's take some other examples. So say when volume by surface decreases, that is you are miniaturizing, so friction becomes larger than inertia. Why friction becomes larger than inertia? Because friction is actually proportional to surface area, whereas inertia is proportional to volume. So basically V by S is decreasing, so inertia is becoming less important than friction. Heat dissipation becomes like dissipation increases, heat storage reduces. So this is again from like another interesting thermodynamic system. So suppose you are looking at macroscopic thermodynamic systems to microscopic thermodynamic system. So let's say you are trying to develop thin film batteries. Right. So in this kind of an argument is going to be very useful immediately, because we know that as we go to smaller and smaller dimensions, now dissipation is going to increase and charge storage or heat storage is going to reduce. So therefore we are going to come across newer challenges when designing thin film batteries. Okay, so that can be argued upon by a simple scaling argument. We don't have to go very complicated. So that's the overall idea which I wanted to convey. Similarly, energy coupling is preferred over energy storage for the same reason. So why? Because as smaller sizes, because the volume of the object has reduced, so your energy storage has reduced. So therefore you would rather like to transmit energy from another physical system to that micromechanical system, right? So therefore energy coupling is preferred over energy storage. So that's another idea. So now let's see how these electrostatic forces come about. So it turns out when we are talking of electrostatic force, right, so we are basically worried about q1 q2 by r square times something which is constant. So although this constant had a unit, as we saw in last discussion, last section on units and dimensions, but practically like that is a constant, right? So whether you are talking about charge on a sphere, to charge on a cube, to charge on something else, right? The constant which is in front, right, which comes into play when you are talking about uh, electrostatic force of attraction between two such objects, this is still a constant, so we don't need to worry about. And this charge is going to be proportional to the volume, right? Because there would be some charge density times volume. So therefore, like electrostatic force, if we see, this q is going to be proportional to length cube, and r square is therefore proportional to length square. So therefore this electrostatic force is basically length cube into okay, so wait a second. So here this is, sorry, charge resides on surface. I'm so sorry. So charge is going to reside on surface, so this charge is going to be proportional to length square, right? So therefore what will happen is like this force is going to be length square times length square divided by length square. So therefore the dependence, the scaling law which is relevant when talking about electrostatic force is going to be length square. Similarly, when we are talking of pressure, right, say pressure would be force per unit area, right? And force is going to be proportional to mass and proportional to acceleration, right? So mass is going to be proportional to length cube. So this is like mass into acceleration by area, but mass is going to be proportional to length cube, and acceleration is going to be proportional to length, and area is going to be proportional to length square. So therefore the scaling law being followed by pressure is going to be length cube times length divided by length square. So therefore this is going to be about length square, and so on. So I would leave this as a homework and this as a homework and this as a homework, which will require a little bit more reading. Huh. Say when we are talking of gravitational force, again it is very easy to see, like what we are really interested in is g m1 m2 by r square. G is a constant, like the quantities to which you can put pure number irrespective of the physical scenario involved. You don't consider their dimensionality while doing a scaling analysis. So that is an important point. And m is going to be proportional to length cube, right? And r square is going to be proportional to length square. So therefore this overall is length cube whole square by length square. So that is going to be proportional to length to the power 4. So like these kind of scaling analysis are really useful. I can see that the clock has struck 4 o'clock, so you will be busy with another class, so we will stop at this. So however, before we stop, let me just kind of end with these remarks that surface tension is annoying for non-fluidic applications. Okay, so this is something which is really like crucial when we are going to miniature sizes. We have to be really worried about that. And similarly, electrostatic force is more interesting than magnetic force as relevant length scales goes down. So therefore, it turns out when you are looking at physics at micron scales, right, then magnetic field is a less preferred source of applying force than electrostatic field. Okay, so that is again the reason why you must have seen maybe electrophoretic movement of cells, right, from one pad to another. You would have seen at times interesting demonstrations where cells are kind of manipulated using electrophoresis, but magnetophoresis is not really used. Okay, because magnetic field is much weaker